All right. This is the Gradle, and the one I just downloaded the Excel file. I don't see you have the, but I just show you how to do it. Okay, you can go back home and practice. Okay, all right. And this is a Gradle's, and I think I need to convert this one, the Excel file, to the very okay. I'm sorry. Excel, why I cannot do that at the same time? I'm already open it. Okay, let me see. Okay, and I need to convert it into the latest. I need to convert it into the latest Excel file. My downloaded is the old versions. I have to convert it into, and I change. I don't want it to be the copy. Okay, then store in the desk. Okay, then I do have the latest, the new version of the CONS8 Excel file. And for Gradle, what I do is just drag in. I just drag in. Then, since this is all the data is from the very beginning, okay? So A, B, and actually I wanted all this information is from C to E, right? Okay, so in that case, I will start to import it. I can just say the third column and the first row, because I really wanted to have the variable name. So the third column, so I would say 1, 2, 3. The first row, and OK. Okay, so COLA and YD is already in, and there's a constant is still in there. Okay, then from now, this we consider this is a cross-sectional data, because this is different students. So in the future, if we work with the time series, then in that case, if I have some data from Excel, I need to say yes here. Since the question asks, do you want to give the data a time series or panel interpretation? If I do have time series data, then I say yes. Now is no. Okay? Then in this case, did you see the model? Okay, if I hit the model, then ordinary is good. There's a lot of methods, right? So the same as eViews, okay, I have a lot of methods. Ordinary least squares, and I need to tell the computers that what is my dependent variable, use the arrow. Highlight the variable and use the arrows, okay? So this is YD and LA as my X variables, then I put it in. Then I'll type it. Okay, hit OK. Then this is my first model with 2 variables. So we can do that. You can play that with home. At home, then you do have the R square, adjusted R square, p-values, F statistics, everything, all of the information. Does that look like eViews? Yeah. So you can double check what you work, and there's many functions here. We'll show you gradually. Okay. Okay. So this is the Gradle. I think it's also useful for you because you don't need any license. This is universally free. Okay. So let me go back my examples. Okay. I'll get rid of the Gradle. Okay. You just do it at home. You play with that. Okay. But at the same time, in the class, sometimes I will just show all the Gradle's procedures if necessary. Okay. All right. So let me get out of the Gretos. And then if you have any questions about Gretos, you can ask, even from the lines, our class lines. Okay, and for Gretos, if you save your file, let me do this one. File, then I save as. Okay, then I'll say. I also can give the same name, CLNS 8 and S8. Okay, 8. Okay, then I'll save it in my desktop and save it. Huh? Did I save it? I did? I hope so. So let me check whether, if I have that, did you see this one? This is Gretel's data. Gretel data, GDT is Gretel's data. Okay, so that one will be my eViews is WF1. This is from eViews. Okay, with this one, this is eViews, and this is Gretel's data set. This is Excel. So many data sets, but it works for different packages. Okay, all right. So let me get out of eViews. All right. Okay. Then I'm talking about this example. So let's go back to this example again to see what happened if I do have the data we just show. The result is something like the 8.13. Okay, I know that important variables REG is beyond. It's different from our expectation. The sign is different, and also it's not significant. So what do I do? And from our authors, okay, I think this is from 8.13 to 8.14 is a big, it's really a big change. And you have to you have to give your own self reasoning to say that, why do I use change it from A13 to A14? So if you see you have the sign is different, like the last semester we are talking about in chapter 6 and chapter 7. Chapter 6 is talking about the x variables. If you have some missing x variables, it can have the consequence like this one. I mean the opposite sign. Important variables with the opposite sign. Or if you have some specification error, means the functional form is different. Okay, the functional form is different. It also can have the result. And in this chapter 8, it shows that if you have multicollinearity, it can happen to have the different signs with important variables. Okay, and in this case, we are going to talking about the multicollinearity. So look at the two variables. One is called UHM. The other one is REG. What is the definition? What's the, is the real definition? Let me say it again, okay? UHM is urban highway miles within the state. So it's just only urban highway miles, okay? And REG is motor vehicle registration. So it seems that the highway miles is some part of information, and motor vehicle registration. No matter you live in town or outside of town, you also need to have car to go the routine work or run some short distance journeys, right? So it seems that registration, they are highly correlated. But we may just leave one reg, these variables, and although this UHM is significant, okay? Although it is significant, but since REG is more related to the consumption of the petroleum more than the UHM, the reason maybe this REG in 8.13 equation is not significant and with the different signs is because of the highly correlation with the UHM. Therefore, you try to drop UHM and leave REG and run the regression again with this two variable only, okay? And look at the result. And I like to say that, the sign here is wrong. I mean, wrong is not exactly, for output, this is positive instead of negative, this typo. I mean, the PPT has typo. If you look at our textbook is positive signs instead of negative signs. Okay? So look at the result. You need to change this a positive sign. Does the sign all follow the expectation? Yes. Okay? And look at this one, tax. And the number of motor vehicle registration, these two variables is not really related, right? Okay? So this variables is not related to this variable, and the changing from equation A, the result from 8.13 to 8.14, it seems that the t value is not that change, not that big change. Okay? But the REG is changed from negative to the positive. And the significant for t value is really big. It's 15.88. Did you see the result here? Okay? And adjusted R square is smaller. The 18 is higher than the 14. So there we have some information lost because of we drop UHM. Well, but it really doesn't hurt much. So that's why that's saying that we drop an important variable. So looks like very important variable, and actually it's important. So now we don't have the another variables. If we have data, I like to run one drop REG with UHM stays in the model, but we don't have it. But the author, I think, convinced us that, with REG is more important than with UHM. So they didn't provide the models with UHM. Yes? Oh, I think this is just... Oh, well, I really like to say something about that, okay? First of all, we all have to follow the theory, okay? Follow the theory and follow the literature, okay? And it seems that UHM and REG is really, it is also important. And it's hard to really, drop one of them. So in this case, if, like all of, I have to be honest that if I am a researcher, I will run 3 models. Okay, one is with REG but without UHM. The other one's with UHM without REG. But I also, text TAX is all included. Then I like to see what looks like. Okay, then I choose the one which seems pretty good. Okay, but in that case, if I have the one with UHM without REG as another equation here, but those two are very good, then what is your decision? What is your decision? I think this is, really, it's not really definitely answer, but our authors say that UHM with REG is better than UHM now, according to the definition, because UHM is only the urban highway miles, but the REG is number of motor vehicle registration. So urban highway miles means just only, if you live suburban, it's not urban, right? So it's a short distance, but you still need to have a car, right? So I think that's reasonable. This reason is reasonable. So the answer to say that whether we will try many models, okay? In this examples, we have 3 variables. Then we can run 3 models. If you have 10 variables, if you do that to run all the equations, we say that is fission instead of correctly find the models. That's fission. Do you understand what's the meaning of fission? Fission. FISHING. Means, you're just looking, whatever your decision is based on the output. The idea of fission is you really want to see the output to decide the model, right? But the sequence for research is according to the theory, then decide your variables. So you cannot go to the output, then go back to your theory, then to choose the model. The order is wrong. And this is it's not, we all say that when we do the research, we have ethical issues to deal with. So this maybe is not that serious as ethical, but somewhat, you are looking for you think is better result. But I will say something about these problems. Not all of the problems have the same idea, but I'm saying that we will say that how to detect the multicollinearity problem, and also we'll say that then what's the remedies for multicollinearity? Okay, when we say the remedies for multicollinearity, we will say that actually the multicollinearity problems is not from the population, it's from data itself, because we're using data to try whether the population is there as a consequence, or there's a relationship between X variables and Y variables, right? And we're using data. So if you can collect the different data, maybe your multicollinearity problem disappear. If that is the case, then actually multicollinearity, you don't have to do anything about it. Just leave it there. I said, how great if I find the multicollinearity. I can just leave it there. I don't have to just do nothing. But actually, for multicollinearity, since it is the data set problems instead of populations relationship problems, so if it's possible to get another sample size, many of the situations we're not able to get another sample size, since get another sample size is expensive. You need to have time. You need to put on the labor, your labors, your times, and many costs. And maybe you are not able to get the data itself. Okay, so for multicollinearity problems, if according to a theory, you need to have these two variables, then just leave it there. And since this is a little bit, serious with these two variables, so I'm going to go on to how do you detect the multicollinearity problems. Okay, in order to answer, some of the questions how do we deal with that? What's the remedies? Okay, then how to detect it? I think according to the consequence, we can see from the consequence to go back to detect these multicollinearities. But first of all, we have some guidelines or criteria we can see, okay, from the 8.3. The section 8.3 is about the detection of multicollinearity. The first things you can see the simple correlation coefficient. What do we mean by simple correlation coefficient? Simple correlation coefficient is the pairwise correlation coefficient. Pairwise. So now we have this two variables, in our examples. Okay, we have two variables. Okay, let's see how do we get correlation coefficient from e-views first. Okay. Let's see my e-views here. I need to go back to my, okay, let me get and e-views. Where can I get to my data, original data here? This one? Hey, okay. Okay, if I wanted to see the pairwise comparison, correlation coefficient from e-views, I need to highlight my variables. In this case, is LA and YD. Okay, then open as a group instead of equation. Okay, group as a group. Then using, I think it's view. Let me see, view. Okay, I check view, then covariance analysis. Yes, covariance analysis. Did you see that? Covariance analysis. Then click correlation instead of covariance. Click correlation. Okay? All right? Then hit OK. Let's see. You know how to read this matrix? I have 2 row and 2 column with LA and YD. And the column and row for the diagonal parts is all equal to 1, right? What do we mean by that? LA against to LA itself. So of course correlation is 1. Okay? You all know the range of correlation coefficient? Huh? -1 to +1. Okay? Remember that. The coefficient correlation is between -1 to +1. Okay, and with the 1 is, since it is itself, so of course it's +1. It won't be -1. Okay, then off the diagonal you can see this two, since I just have 2 variables. If I have more than 2, then this matrix is bigger. Okay, like if I have 9, I have 3 columns, 3 rows, and in terms of 9 cells. Okay, now I have 2 variables. So you'll see that LA with YD or YD with LA from the off diagonal actually is upper triangle or lower triangle, which is matches. Okay, so you can see one upper triangle or lower triangle, either way is okay. Okay, so with this 2, LA and YD is 98, 0.986 is really high, right? So if we have high simple correlation coefficient, it signals that you have multicollinearity problems. So this is one way. Okay, and you will say that how high is high? How high is high? Yeah, many books, okay, say absolute value of the coefficient, since we have negative to positive, right? So the absolute value of the coefficient is bigger than 0.7. You have to start to thinking about the severe problems of multicollinearity. But different authors, some say 80%. Whatever, I think, this is a signal. Okay, this is a signal. Okay, but I'm going to say that with 2 variables, okay, with 2 variables, just 2, either one of them is the same correlation coefficient. And this is, since there's no other variables. But sometimes if I have 3 variables, then maybe these 2 variables are affected by some number which is not included in this model. Okay, it happens, right? Or although the numbers included in the model, but actually the relationship of this one is only calculate the relationship between these 2 variables, neglect the rest of the x variables. Okay, understand what I'm saying here? We'll just calculate the relationship of these 2 x variables, neglect the rest of x variable in the model. Therefore, I'm thinking about these 2 variables. I didn't thinking about the rest of the x variables, although we don't have the rest of the x variables in this model. But many situations I do have the rest of the x variable in the model. So pairwise correlations, just thinking about the relationship, but neglect the rest of the x variables. So it may not be that correct. So this is the drawback. Although I can see the criteria, for this one, pairwise comparisons. So some authors will say partial correlations. Partial correlations. What do we mean by partial correlations? Partial correlations is fix the other variables. I consider it, okay? I consider the rest of the x variables, then calculate the relationship of these 2 variables. So it is not in our textbook, but in this province they provide this kind of information, but not in this book because that's more complicated. So I'll show you my material, okay? Let's see what I have here. Okay, let me see the partial one. I'm afraid of give you some math here, but I don't. I'm not sure for engineering. Maybe you're okay, but my business students, I'm pretty worried about them, and I don't want to scare them. Okay, so look at this one. Okay, look at this one. This is what we call pairwise correlation coefficient. So I just look at x and y. Whatever I have any other, this xy means the x variables. This y doesn't mean the correlation with my y variables. Okay? Remember these notations. Don't mix this xy with the y in the regression model. Okay? So this one is the what we calculate the correlation coefficient. Without knowing this formula, we can get it from the output, so we don't really have to know the formulas here. But I want to show it is the pairwise. Not pairwise, is partial correlation coefficient. And I say that the drawback. Let's see this with the red ink, the sentence with red ink. It is not good practice to rely on simple or bivariate, means pairwise correlation coefficient, because they do not hold the other variables in the model constant. Means that they didn't think about the rest of the x variables, okay, while imputing the pairwise correlations. Therefore, we have what we wanted to show is a partial correlation coefficient. And this one is to hold other variable constant. We have to compute the partial correlation coefficients. So for example, I have, like this one, the red ink. The partial correlation, look at this one. If I have three variables in my model, 1, 2, 3, I mean x1, x2, x3, okay? I wanted to know the correlation of x2 and x3. Then, since x1 is still in the model, right? So I look at the notation, use r, x, 2, 3, and dot 1. This 1 means holding x as a constant, means after removing the influence of x1, means considering. It's already considering x1. We hold this variable fixed, okay? Then I can calculate the partial correlation with x2 and x3. So in that case, look at the formulas. It's getting pretty complicated. Look at this one. So if you compare this 2 and 3, it's become, really is the number 3 is getting complicated, because the number 3 is using what I have from the formula 2 for each pair of the 1, 2, 3 and get the partial correlation. Okay, and I looked through all the e-views and looked through all the Gretos. They doesn't provide partial correlation coefficient. But since you're engineering, so you can write the program, it's not easy. It's not difficult to using the formulas. Type it. Like the programming is all use, put all these formulas into the computers, then they can calculate the partial correlations. So I think the easier way to do it is what? I'm using Excel. I'm using Excel to do the partial correlations. So let me show you what I did, okay? So this is what I did. Okay, this is actually I'm working this one as using the data I give it to you, chapter A-1. And I'm going to use this data as your some part of assignments. Okay, I'm using this one. Okay, now I'm working with some small parts of the X variables. So I'm using age, education, and experience as my X1, X2, and X3. Okay, understand what I'm saying here? So the upper one, this one, is the pairwise correlation coefficient, is the matrix. Okay? Then I'm calculating the partials. Using this partial correlation to compare with my pairwise comparisons and let you see the difference. Understand what I'm saying here? So this is this matrix is pairwise correlation coefficient. This is partial correlation coefficient. So this means X2 and X3 using X1 as a constant, and is holding X2 as a constant, and the relationship of 1 and 3, holding the third one as a constant, X3. Then this is 1 and 2. And you can use these numbers to compare with the pairwise comparisons. Okay? And how do I get these numbers? I just, plug. Let me write it down here. Okay, I just plug all this, the equation with 3 to write down the formulas to calculate the comparison. Yes? You mean matrix? You mean this one? Yeah. Like age with education means what? 1 to 2, right? 1 to 2. So from 1 to 2 is negative 0.05217. So one, look at this one. This is 1 and 2, right? But I'm holding the third one as a constant. Then it turned out to be pretty similar. So means what? Means what? Although I have the third variable experience, but that really doesn't affect the correlation between age and education. You know, when we consider partial correlation, we're thinking about the third one will affect the relationship between X1 and X2, right? But actually, these numbers tell us experience doesn't affect the relationship between age and education. And this one too. This one is 1 and 3. So age and experience with education as a constant is this one, right? And age as an experience without thinking about the education, the correlation is 0.48. It's pretty close, right? But look at this one. This is 2 and 3. So education and experience, and holding age as a constant. The relationship is positive, 0.011 something. But look at the original one. If I look at education and experience, it's negative. So this one is from negative to positive. Okay? I think this example tells us that partial correlation coefficient is thinking about the rest or the third of the variables affect the relationship of these two. But some of them, the third one, will not affect it. But some is really affect. Okay? All right? And the reason I do this one is also, I like to show the numbers for the difference of the number of pairwise comparisons and partial pairwise correlation coefficient and the partial correlation coefficient, the difference of them. And since I cannot get it from the computer output, so I'm using eViews to do this example. I know maybe some other packages can do it or using. Now you can use the Python. Yeah. Did you? Oh, you already did? Do you have the same as I did?
Oh, this is for the
Oh, the
other days.
the different data. Okay, okay, okay. So this one is using the formulas. You do the programming, or you can just have the commands. Okay, okay. You can have to have. No, I cannot get it from eViews or Grados. Maybe you can find it out from eViews. Yeah, or from Grados. I couldn't find it. So if you find it, tell me. Tell me. I'm using eViews to do it. Okay, it's good to always use the command, right? You don't have to write down the formula, programming it. All right, so this is the pairwise comparisons. And, there's one which is always used in the multicollinearities, and which is called VIF, variance inflation factor. And, there's something I think I'm ready to say, explain it in more detail. So I'm going to leave it next time. Go back and review what I have it today. Then after next week, we will have assignments. After next week, and maybe I'll give it to you, the questions soon, okay? All right, you will have time to do it at home. Any questions for what I'm teaching today? I think you need to go back and review it. Okay, it's important to review it. Okay, thank you very much.